In the previous video, we introduced the idea of mutual inductance between two coils of wire. In other words, we quantified the strength of the inductive connection between two coils, allowing one coil to induce an EMF in the other. So the basic idea there was that a changing current in one coil produces a changing magnetic field through the turns of the other coil, and then an EMF was induced in the second coil by way of Faraday's law. Now in this video, we derived the self-inductance of a solenoid. So a single coil actually experiences an induced EMF when the current changes, because that current generates a changing magnetic field through its interior, which means a changing magnetic flux. And again, Faraday's law tells us there should be an induced EMF opposing the change in magnetic flux. So in a sense, any coil is constantly fighting itself to slow changes in current, and that's what we're going to quantify in this quick derivation. So I've set things up with a picture of a solenoid. And the way the current is flowing here, it's going up the near face of the solenoid and down the back of the solenoid, and of course looping around many times. So using our previous knowledge of the magnetic field generated within a solenoid, we can infer the interior magnetic field is currently pointed to the left. And I'll post a link to my main solenoid video if you need a refresher on how to use the right hand rule to infer the direction here. So of course we need a changing magnetic flux if we're going to see any induction effects. So I'm going to assume that the current is increasing. And we write that as a time derivative, di dt is greater than 0. Okay, so the leftward solenoid field is getting larger. And according to Lenz's law, there's going to be an induced EMF attempting to reduce this effect. In other words, the induced EMF acts to drive current in the opposite direction in an attempt to create a rightward magnetic field. And I've labeled that field B induced. So that induced EMF isn't winning, by the way, as we've applied a voltage to this solenoid sufficient to guarantee that the current continues to increase. The point is that the induced EMF is attempting to drive current in the opposite direction to fight the direction of change in the magnetic field. So the induction effects are going to slow down the increase in our current. Now, just like we did for mutual inductance, the self-inductance, or simply inductance of our solenoid, is found by relating the induced EMF to the rate of change in the current in the coil. So we define our self-inductance L by this relationship that the induced EMF is equal to negative L times di dt, where again, remember di dt is just the rate of change in the current. And the minus sign there, it just indicates that the induced EMF acts opposite the direction of increasing current. So that L in our relation is called the self-inductance of the solenoid, and we can figure out how to calculate it by using Faraday's law. And there's Faraday's law saying the induced EMF is equal to the negative of the rate of change of magnetic flux through the coil. So all we have to do is apply Faraday's law and show that the induced EMF is proportional to the rate of change in the current. And then that constant of proportionality, that's the self-inductance of the coil, which we ordinarily just call the inductance. So we start with Faraday's law, and then we're going to put in the details about the magnetic flux. Remember, the magnetic flux is just the magnetic field strength times the area. And using our previous result for a long solenoid, the magnetic field inside of a solenoid is given by this piece right here. That's mu naught times little n times I. Now that little n means the number of turns per unit length for the solenoid. So that piece is the strength of the magnetic field. And then this other piece on the right, that's telling us the area that those magnetic field lines are actually passing through. The big N there tells us the number of turns of wire. And then the A is just the cross-sectional area of any one loop of wire in this solenoid. Now again, that little n stands for the number of turns per unit length for the solenoid, so we can replace that with the total number of turns divided by the length. So here, that's all we've done is make the replacement that little n is big N over L. And then we realize that all of this stuff is constant except for the current. That's the only thing that's time varying. So we should be able to factor everything out except for the little I. So while I collected all those constants out in front, I also combined the two factors of big N into an n squared and wrote everything as a single fraction. And this is exactly what we were looking for. We just managed to show the induced EMF is proportional to the rate of change in the current in this coil. And we call that constant of proportionality the inductance of the coil. So the self-inductance of a solenoid, we call that L, and it's just given by mu naught times big N squared times A over L, where that big N is the total number of turns in the solenoid, A is the cross-sectional area, and L is the length. So the inductance of a coil can be thought of intuitively as how strongly that coil will resist changes in current. For the same rate of change in current, a larger L means a bigger induced EMF fighting that change. This allows us to think of inductors as the source of a kind of current momentum in an electric circuit, and we'll see that behavior in the inductor-resistor DC circuit as well as within a variety of AC circuits. In the next video, we derive the self-inductance of a thin toroidal inductor. In other words, for a donut-shaped coil, we assume the cross-section of the donut is small compared to the main radius, and that allows us to avoid using an integral for the flux calculation. And of course, we can't resist generalizing that result later on because integrals are so fun, but for now I'll post a link to the thin toroid video at the upper left, and I'll see you there.